2, and theta is minus x dy. The Clebsch variables are phi 1 d, d phi 2 df. This is what Clebsch did in 150 years ago, 170 years ago. So now we look at helicity. If V admits a representation in terms of Clebsch variables, the helicity must vanish. The computation is half a line. The helicity is by definition V flat wedge dV flat, the integral of this three form. All I'm doing is I pull it back, and this is obviously zero because theta, wedge theta, is a three form on a two manifold. There is nothing to say. This is zero. If you have Clebsch variables, you have no choice. Helicity must vanish. What happens if we do it? Well, it's not exact, but it admits a pre-quantum bundle. I do exactly the same thing. I write the momentum map, this generalized momentum map. Suppose there exists a phi 0 such that phi 0 star is trivial. Then for any phi in the connected component, which I call f phi 0 or phi 0, the bundle phi star L is trivial. Since the composition, this is the Chern class, is a continuous map. Hence, the restriction to f phi 0 takes values in the level set of the Chern class, which is omega 1 over omega 1 closed with integral periods. By duality, I'm going to do exactly what I did before. I'm going to write V flat minus phi star nu plus theta. Who's this theta? Theta now is a one form which is closed with integral periods. And by the slight abuse of notation, because it's very intuitive, phi star theta denotes the one form on M that is induced by the pullback connection phi star theta on the trivial bundle phi star L, right? If you're a geometer, you immediately see this. So the Euler equations are on this quotient. In fact, the Lie derivative of a one form beta with integral period is exact. Here is the proof. You integrate over gamma L x beta, you just use the Lie derivative formula, change variables. Instead of putting the pullback on beta, you put it on the integrand, on the domain of integration. And this is an integer, so there is no derivative, right? So the Euler equations that were initially here implies that the class beta is here, which is the first cohomology with integral coefficients. This is constant in time. So that means that the interesting part of the motion in fluid dynamics takes place on omega 1 over omega 1 closed Z. I'm telling you things that I think people somehow know, but nothing has been explicitly written. However, it's only to define an inertia operator for small time. So you don't get away with the usual inertia operator because this bundle, the RAM cohomology over the RAM over integer cohomology, is only locally trivial. It's not globally trivial. Now, what do I do with helicity? So what is helicity or Hopf invariant? Has to do with one forms. And you take the one form, alpha, wedge d alpha, on a three manifold. Now, those of you who have done mathematical physics, and I know several of you in the audience, if you forget that I'm talking about hydrodynamics, you would say, wait a moment, you're doing a billion Chern-Simons theory. Yes, I am. And this was already observed by Liu and Rika. The Chern-Simons functional admits a well-known generalization to non-trivial circle bundles. This was already known long time ago in a paper by Fried, Moore, and Siegel. So there is a fundamental connection between hydrodynamics and Chern-Simons theory. So for a differential character H, there is an operation which I'm not going to explain. It's a long story. But it adds the degrees. H star H is a fourth order Chern-Simons character. This induces automatically, that's by definition, a homomorphism of the cycles with integral coefficient to the circle. So we can evaluate it in particular on a three cycle. You write the evaluation as integration in order to have the intuition that this is what you're doing. And you get a generalized helicity. So here we go. So what is the helicity in fact? is a map from the second order Chigger-Simons differential character to the circle, obtained by taking the star product of the character and integrating. How much more should you say here in fluids? You should. That there is much more topology going on than meets the eye. And it's non-trivial topology. Let me summarize. I'm going to put in one slide. By now you got my color scheme. Blue is definition, and the red is the theorem, so lemmas, things that need to be proved. So I take a compact three-dimensional boundaries Riemannian manifold, oriented by the Riemannian volume, a solution V of t of the Euler equations, projects via take the class of the drop of the form that's going by dropping the index by the metric to this quotient omega 1 forms of a closed one from these integral periods to obtain a solution of the system which you know, but the classes are now different. It's not omega 1 over d omega d functions, is this much more subtle quotient. I take f omega a two-dimensional symplectic manifold. It's admitted to pre-quantum U1 bundle with a connection. The natural action of the diffeomorphism group on this space of functions preserves a symplectic form and has a group-valued momentum map. I wrote it by now 3 times. Assume there exists a phi 0 such that the pullback bundle is trivial. Then the restriction of J to the connected component takes values in this quotient and yields generalized Clebsch variables for the projected Euler equations above. These, where V flat is written here. Here I wrote how you obtain Clebsch variables. Every vector field admitting such a generalized representation has integral helicity, not necessarily zero. So why does this work? I'm hiding something which is serious, and these are the group's valued momentum maps. There is no way I can tell you what it is. The theory is quite elaborate, but I can show you where it comes from and how we found it. And for this, I need to give you a crash course on Poisson-Lie groups. This is due to Lou in her thesis and Lou and Weinstein. So a Lie group is a Poisson-Lie group if it is simultaneously a Poisson manifold and a Lie group. And the multiplication and inversion are Poisson maps. I denote by this script pi the bivector, the Poisson tensor. So this is a Poisson manifold. What is a Poisson action? Well, it's an action such that the arrow itself is Poisson, which means automatically that the groups, the group diffeomorphisms do not conserve the Poisson action. The arrow G and M into M is Poisson. And this is a Poisson manifold. This is the standard product of Poisson manifolds, in which you take functions on the first factor, on the second factor, and you declare that functions, that these two functions commute. And then you just compute everything using Leibniz rule. So here is what is known. The Poisson tensor pi G of a Poisson-Lie group with Lie algebra G necessarily vanishes at the identity, which then allows the definition of an intrinsic derivative, call it epsilon, from G into G wedge G by epsilon of A, the Lie derivative of the Poisson tensor at E, where X is the vector field, which is totally arbitrary, such that the value at the identity is A. And this denotes the Lie derivative. It turns out that it doesn't depend on the extensions. You must prove this. Dualize the map. So you get such a map. This turns out to satisfy the Jacobi identity. Therefore, G star becomes a Lie algebra. So in a Poisson-Lie group, G star is a Poisson manifold, that's a Lie Poisson manifold, and a Lie algebra at the same time. The unique connected and simply connected Lie group G star, whose Lie algebra is G star, is called the dual group. The Lie group G star has a unique Poisson structure, pi G star, relative to which G star is Poisson-Lie group, such that the intrinsic derivative of this one is the Lie bracket on G. In other words, if you go to one connected groups, so connected and simply connected, G and G star completely determine each other. It's a completely symmetric story. Okay. Now, with these tools, we define a momentum map. So I'm going to copy the momentum map down exactly as we do it. Now, depends on the sign conventions that you have. Okay? So here it is, a smooth map J from M into G star, the dual group, not the dual Lie algebra. If it exists, it's called the momentum map of the action if this equation is satisfied. Now I have to tell you what every symbol means. A star is the fundamental vector field, right? Or the infinitesimal generator vector field. You take the exponential of TA, you let it act on M, you get a curve, take the derivative at 0, you get a tangent vector, do it at every point. What's the second term? So that's the first term. The second term, you have to put in here something. So this is a form. You have to put in also a form here, right? Okay. So what we have to do? So G is the dual of G star, which is the Lie algebra of G star, as we discussed. We think of A as a linear map on G star, and hence it defines a unique left invariant one form, AL. You pull it back. That's what you need. Because this one is on M. Pi is a bivector, so you have to put a form here. You have to put a form here. This is a vector field. So if you apply a form, you're getting a number, right? Okay. So assume that this is symplectic, with symplectic form omega, which is the inverse of the Poisson tensor, because I'm telling you that it is symplectic. Write the definition in this case. So let's do it. So I'm going to simply put here a tangent vector, call it x index M, and evaluate at M. That's what I'm doing, right? That's the left-hand side. Omega M, xm, A star out M. Okay, that's what I'm doing. Now, your definition is in terms of the Poisson tensor. So I invert everybody that I can. Forget these symbols. All I'm doing is I'm inverting. Sharp means index raising operator by the Poisson bivector. Okay? So you already see that things are doing okay, because if I take this and apply it here, it disappears. I get just xm, right? Okay. Now all I'm doing, I'm applying the definition. I just write this. And it's in the wrong place, so it picks up a minus, right? Is this. What do I do next? Well, I know how to pull back. So it's ALJM, tangent map of this. Well, what is AL? I just told you what it is. I take A, I have this derivative, bring it to the identity by the derivative. So this object here, in fact, this is a tangent map, but I'm not writing it again because it's too much writing. This is the left logarithmic derivative. Now I want you to look at this relationship. That's what I got. This relationship has forgotten that G is a Poisson Lie group. When does this relationship make sense? If I have a map M into H with values in an arbitrary Lie group, as long as there is a duality between the Lie algebras of G and H. This is exactly what how I'm going to define the momentum. Okay, so let's do it. That's going to go very quick. A dual pair of Lie algebras, not necessarily finite dimensional, consists of two Lie algebras G and H, which are in dualities through a given weakly non-degenerate bilinear pairing. Call it kappa. I'm using notation that reminds me of semi-simple Lie algebra theory. Right? If you see kappa, you think, killing form. Yeah, sort of intuitively, that's what I'm doing. And I'm writing H to be G star because I think in the back of my mind, even though that's not true, that H is the dual of G. So two Lie groups G and H are said to be dual to each other if there exists a bilinear form at the level of the Lie algebras. Example, if H is abelian, then add star mu is trivial. And this is going to ultimately give me, as I'm going to state in a moment, the usual momentum map. How about group of volume preserving diffeomorphisms? Here is a compact manifold with the volume form mu, same notation. G is volume preserving diffeomorphism. It's a Fréchet Lie group. This is already known long time ago by Hamilton. Its Lie algebra is divergence with vector fields. I kill the boundary so that I don't have any trouble, right? So I identify omega m with dimension m minus 1 closed forms on M. How? Take the interior product. Okay, I take the quotient. This is the quote-unquote regular dual. And what is the pairing? Here it is. The coefficient in the front is done for convenience, so I don't carry minus signs with me around. This coefficient minimizes the amount of minus signs that I have to do in computations. So this is it. Ix, A alpha on mu. I interpret alpha, connection over principal circle bundle. From this point of view, this quotient parameterizes gauge equivalence classes of circle bundles with connections. We are coming the third time to the same conclusion. It's the same object all the time. So I think of this as a Lie algebra of the abelian Lie group of differential characters. So now I have a dual pair. That's what I said before. The dual pair of Lie groups, the diff mu m and the abelian group of Shiger-Simons differential characters. If you do it for symplectomorphisms, but I'm not going to do it, I'm running out of time. This has to do with Lagrangian embeddings. It's the same type of construction, but now you're going to ask what curvature means, and this is higher differential geometry. I don't want to go into this, but it works. So both diff mu m and diff omega m have abelian dual groups, and here they are, and they're usually denoted like this because they're Lie algebras with fracture letters. This is what we saw, and for symplectomorphisms is this one. Now, if everything would be finite dimensional, you would say, "Oh my God, I'm on a roller coaster," because now I applied Drinfeld's theorem, which states that there are essentially unique connected and simply connected Poisson Lie groups whose Lie algebras are x mu m and x omega m. But I'm not in finite dimensions, I'm in infinite dimensions. So not only is Drinfeld's theorem not known, but it's not even known in this example. We do not know if these groups carry a non-trivial Poisson Lie structure. I talked to all the experts in Poisson Lie groups. They don't know it. We tried it ourselves. It's not known. Worse, I don't even know if there is any Poisson structure. Forget the one that comes from this one, from the bialgebra structure. Forget anything. In spite of all these troubles, the theory still works. It's absolutely amazing. So what do I do? How do I get the group valued momentum map? Very simple. I take that formula and impose it. I say I A star omega is kappa A logarithmic left logarithmic derivative. Example, if I take the dual group to be the dual of the Lie algebra thought of as an abelian group under addition, and kappa is the duality pairing, finite or infinite dimensional, and this relationship is written this way. That's the definition of the momentum map. I have recovered the classical momentum map. If you have a bi-invariant form, then of course G is replaced by G star. The Poisson momentum map for Poisson Lie actions, we know it works because that's how I constructed it. But there are others. There is the McDuff circle valued momentum map. There is the Condezot-Dazot-Molyneux cylinder valued momentum map, etc., etc. I'm not going to go into them. They all are particular cases, all of them. Now, the question is, am I allowed to call this a momentum map? And your answer is yes, you use the same definition. Well, that's not really fair. Momentum maps in physics mean conserved quantities. And this is my problem with the usual symplectic terminology of moment. Look it up in Wikipedia. Moment is equal to torque. This is what engineers and physicists, some physicists say, right? So DDT momentum is moment. I would not dare to talk to a physicist and say that moment is conserved. It's like telling somebody that force is conserved instead of linear momentum. It's a mistranslation from French. French has less words than English, and they cannot distinguish between momentum and moment. They add other words to it. Okay, anyway, if it has the right to be called a momentum map only if it has the Noether property. What is the Noether property? The first line in my talk. G invariant Hamiltonian symmetries give conservation laws. Is it true? Yes. If M omega is symplectic G manifold, suppose that the action has a G star valued momentum map, finite or infinite dimension, I don't care. I take a Hamiltonian for which the Hamiltonian vector field exists and has a local flow. In finite dimensions, this is of course true. For Frechet manifolds, this is not usually true. This is more or less equivalent to state the local in time solutions of the corresponding PDE. If H is G invariant, then J is constant along the integral curves of XH. Noether property holds it is a momentum map. Let's go back to the helicity. Here is the helicity. I wrote it in two different ways. Here is a map tau. This is the trivialization map that goes from K forms and K forms that are closed with integral period to the kth degree Chigger-Simons differential characters. This is completely universal. This is the natural transformations. Chigger-Simons differential character come equipped with this map. And this diagram commutes, which is the exponential. And I'm not going to go through this. You can do again a computation, but since I haven't explained to you what the star is, it makes no sense. All I'm telling you is that you can prove that helicity can be an integer. You can have examples. Take the obvious one, M equal to S3 and Fs2. Right? You take the Hopf bundle L theta as the prequantization of S2 and omega. This example exists actually. It's in the book by Arnold and Boris. And what is the feed that goes with it? Is the classical Hopf vibration. Here it is. Right? And there are other knots that you can realize. There is an example which I'm not going to go into because I want to say also something else. There is an example that shows that not every vector field with integral helicity admits generalized Klebsch representation. And here comes the frightening news, that you need to replace the symplectic manifold by a singular symplectic stratified space. If you're a symplectic geometer, you say, sooner or later, this is going to come to bite you. Because when you do reduction, this is what you get. When you do reduction, singular reduction, you're going to get stratified symplectic spaces. So what would you expect? This is the object that you have to deal with. And there is an example based on the ABC flows that show that this is actually the case, but let me skip it. Okay, now we go to reduction. So the reduction, I'm not going to do Lie-Poisson reduction this time. I'm going to do it on the Lagrangian side, which is due to Poincaré. Poincaré was unaware of work of Lie in 1890. He wrote an incredible paper in 1901, which does on the Lagrangian side exactly what Lie did in 1890 in his second volume of Kontinuierliche Transformationsgruppen on the Hamiltonian side. Poincaré doesn't give any references and doesn't give any motivation. In fact, his introduction is funny. If you want to see an English translation, you should look in Daryl Holmes' book in the two volumes. Daryl, I think, is in the second volume, right? So there Poincaré says, I came across this equation of motion in mechanics, which I think is so interesting that I need to tell you about it. And then he goes on. He does it for SO3, and he does it, in fact, for SO3 actions. He does more. But being Poincaré, it is so general that all you have to do is you have to take Poincaré's paper and replace SO3 by G and just copy. It's completely general. However, when you have advected quantities, the situation is much more complicated. The first time it was understood with advected quantities on the Hamiltonian side was in the late 70s. On the Hamiltonian side, it took 20 years till 1998, till Daryl Holm, Jerry Marsden, and myself wrote a paper to understand it on the Lagrangian side. And the reason is because the advected quantities on the Hamiltonian side and on the Lagrangian side are the same. You cannot do on the Lagrangian side what you do on the Hamiltonian side. Anyway, I will give you the extension of Poincaré's theorem for advected quantities because this is what I'm going to use. So first of all, I have to tell you what a semi-direct product is. I have a representation and I work on the right because I'm working with fluids. And these are my conventions for the semi-direct product. There are 16 equivalent isomorphic ways of defining semi-direct products. And all have their advantages and their disadvantages. There is no best. This is the reason why you find every author has his own convention. The Lie algebra is the semi-direct product between the Lie algebra and the vector space. This is the adjoint action, which is the bracket, and I tell you this. So here you see G2x on V1 and here Xi2x on V1, right? The Lie algebra element. V dot Xi is the infinitesimal generator of the action. I wrote it down here. You have to compute the coadjoint action, and I give you the coadjoint action. It has a formula. This is important. What is A dot Xi? That's easy. That's the contragradient representation. Is the action of Xi, the infinitesimal action of the Lie algebra on the dual vector space. And what is this strange object, V diamond A? I'm going to give you a formula. Those who are versed in symplectic geometry know exactly what it is. It is the momentum map of the lifted cotangent action, where the base manifold is the vector space V. Okay, but if you don't know this, who cares? It's a formula. And I'm going to emphasize from now on, because the formulas that come now when I'm going to do stochastics are complicated. It's the formulas at this level of presentations are not important. What is important is that they exist, they are concrete, you can compute with them, and you get results. So the Lagrangian semi-direct product goes like this. I give you a Lagrangian that depends on parameters, V star. For example, the initial density on fluids, the gravitational pull for the rigid, for the heavy top, the magnetic field for MHD, etc. So there is an L from the Lie algebra V star in R, which is obtained by simply acting with a group. Here you act by right translation to the identity, and here you use a contragradient representation, the obvious thing. I give you a curve in G of t, and I give you a curve in psi of t. I take G dot t and bring it to the identity. And I let A of t be dragged by the action. If you take the derivative of this equation, you get this. So you get one equation. Well, one vector equation. Linear equations with time-dependent coefficients, quadratures. Now, the Poincaré theorem for semi-direct product goes like this. With A0 held fixed, LA0 of the Q's and the Q dots, here are G and G dots, holds for variation delta G, vanishing at the endpoints. G of t satisfies the order Lagrange equation for LA0. This is nothing. This is classical mechanics. Everybody knows this. Nothing new. Here is what's new. The constraint variational principle holds delta of L of psi of t, A of t, D of t is 0. Notice, please, A0 here is fixed, here it's not. And A of t is, in fact, this as this expression. We know exactly what it is. Upon using variation delta xi delta A of the form delta xi delta eta delta t minus xi eta, and delta A is minus eta eta, where eta t vanishes at the endpoint. Again, careful. Delta G vanished at the endpoint. It is not delta Xi who vanishes at the endpoint. It is eta who vanishes at the endpoint. And this is equivalent to the Euler-Poincaré equations for semi-direct products. The classical Euler-Poincaré equations that Poincaré wrote down are just this. This is the new term that comes from the objective quantities. Okay. Now, those of you who are geometers, think of delta as dd epsilon, and xi was a ddt, modulo translation. If this reminds you of the Gauss formula, you are right on the nose. This is the Gauss formula for a linear connection on a Lie group that has torsion and no curvature. We all know, and that is taught in every class, that you have the Maurer-Cartan equations, which in fact tell you that you have a principal connection of G over a point, right? But there is a linear connection, which is not metric. It's not metric because it has torsion. Any Lie group comes equipped with a linear connection. It is the Gauss theorem for that linear connection that gives this. So these are, I mean, the geometry is absolutely astounding. This is analysis. I'm talking about a variational principle that is constrained, and the constraint is 100% geometrical. It is the Gauss theorem. Okay. Now, what I'm going to do now is I'm going to simply flash a few things and then just tell you something. What we are doing with Annabella and Xin-Chen, we are on a program. We try to understand how classical mechanical things can be applied in the stochastic world and what do you get. So we want to apply this theorem where the paths G are stochastic. That's all we do. It's easier said than done, of course. You have to be careful what you're doing. So we want to obtain dissipative equation from variational principle. This almost sounds crazy, right? If you do dissipative equation, if you do variational principle, you get conservative equations. You don't get dissipative equations. However, if you work in the stochastic world, you do get dissipative equations. And in fact, it's even more shocking. You can model this. You can decide what kind of stochastic paths do you take, what kind of perturbations do you take, and how many perturbations do you take. You can obtain stochastic ODEs, stochastic PDEs, or deterministic PDEs, working in the stochastic case. For that, you need to redo everything I have told you in the stochastic world. So the first thing you have to do, you have to work with, in the finite dimensional case, there are two levels of difficulties. First, you prove this is all in finite dimensions. So you have to use probability theory with Lie groups. This, if you look in Ikeda and Watanabe and in Emery, you find this. Also on manifolds. So I'm not going to repeat. I certainly assume that you know classical probability theory. So you have to define semi-martingales values in G, for example, and it's very simple. You simply say it's a PT-adapted process such that when you compose it with any f, a C2 function on G, you get a normal, real-valued martingale, semi-martingale on the probability space. And then you repeat the theory. I don't have time to go through all of this. The end result, you have all sorts of derivatives that you have to introduce. They all have to do with the stochastic background that you're studying. So for example, here, circle D means Ito. D without circle means circle D means Stratonovich. D without anything is Ito. We all ran out of D's. All the D's have been used. All the D's and deltas have been used.
Tudor, we're about out of time, so I wonder
Yeah.
if it's a good time to wrap up.
I'm going to finish now. So let me show you the last one. By the time everything is done, I'm going to have an equation that repeats with perturbations P in the stochastic world. These are stochastic PDs, stochastic ODs. The Lipperson equations. There is a variational principle, which is stochastic. Then you want to do Navier-Stokes. And basically what I'm telling you is that I'm pulling a rabbit out of a hat. I can do it and I get Navier-Stokes. Happy birthday, David.
Okay. Thanks very much. So we'll start here in the room if anyone has questions, and then switch to Zoom. Marcelo?
Yes, I have a very general question. You mentioned at the beginning the difficulties of working in the Frechet category. So I'm just wondering, why can't you work with finitely many derivatives, like in Sobolev space, for example?
No, because then, already known by David, right? Long time ago, in 1969-70. It's not a Lie group. If you take H as diffeomorphism or S bigger than n over 2 plus 1, it's not a Lie group. And you can see it's not a Lie group because the Lie algebra is divergence with vector fields of class HS. If you take the Lie bracket of two HS vector fields, what do you get? An HS minus 1 vector field. There is a cure. You can work in inverse limits. Omori did this, right? In ILH or ILB. You can do this. But this is in some sense cheating.
Well, why don't you go up one degree of smoothness, work in HS plus 1 to ensure that the constructions that you need are doable?
Yes, but now you face a nonlinear version of closed unbounded operators.
I'm not.
You don't get vector fields anymore. They're not defined everywhere.
Yeah, but you know, of course, it depends on the constructions that you need.
Yeah, I mean, in Chernoff and Marsden tried to do this long time ago, and they were supposed to figure all of this out. It was never figured out. I agree with you, Gerard. I agree. This is something that should be done. I mean, this is one cure. You go one up, you face the fact that they are densely defined, and you try to do geometry like this. Nobody has done it.
Yeah, but it seems that the Frechet framework worked out pretty well, right?
Yes, it did. It did. If you want to see sort of the master of all of this is Karl Hermann Neb in Erlangen. I mean, he really understands this, how to do the calculus and everything, right? I mean, for example, what is a Lie subgroup? Is it injectively immersed? Is it closed? Is it closed with closed complement? Everything is possible with nothing, closed, and with closed complement. You have so what we call Lie subgroup in finite dimensions splits into 3 classes of Lie subgroups in infinite dimensions, and there you really have to deal with the Frechet category. There is just no way out.
Okay. Any other questions here in person? Other questions on Zoom? Okay, so let's thank Tudor again.
Thank you very much.